Unity in parallel RLC circuits. Let's take a look at a parallel RLC that has a unity power factor. What's significant about this? Why do we care? So 1 ohm resistor with a inductor of 1 ohms of inductive reactance, and then a capacitor with 1 ohms of capacitive reactance. And that would then mean, just due to Ohm's law, that we should have a total of, well, 10 amps here, and 10 amps here, and 10 amps here, which is then going to give us a total current of 10 amps here. Oh, wait a sec. Did I just screw that up? Of course not. Now let's see why that's true. So in this circuit, the watts would be 100 watts, 100 VARs worth of inductive reactive power, and 100 VARs of capacitive reactive power. We know that these values here are going to combine and then subtract from one another on the reactive side, giving us a net VARs of 0. And if the net VARs equals 0, we know that for our power factor, that would then mean that it must be 1. The power factor of this circuit must be equivalent to 1. Okay, well, let's take this information then, and let's sort of ask some questions regarding it as to what happens when things were to change in this circuit. So let's take the same circuit, and I've just written up here the value of watts and VARs for each one of those. And we're going to do the same thing that we did for the series resonance discussion. We're going to say what will happen to the total current, which is 10 amps, if each of these situations were to occur. So first thing, what would happen if we increase the XL of the inductor? Well, think about it following through all the different steps. So if you increase the XL of the inductor, what's that going to do to the current through the inductor? That's right, it's going to make it decrease. And if it decreases, what's going to happen to the VARs of the inductor? Will the VARs of the inductor remain the same? No, for sure, they won't. The VARs of the inductor will go down. If the VARs of the inductor go down, will they be equivalent to the capacitive VARs? And the answer is no, they won't be. And so what we end up with is a power triangle that's no longer horizontal. The power triangle now has a little bit more capacitive VARs. So I'm going to say QC. Little bit more. Power still there, which means S total has gone up. If S total has gone up, what happens to the total current of the circuit? Remember, just use your basic power formulas. If S total has gone up, and we're assuming the voltage remains the same, then that means that the total current must also have gone up. Okay, so let's take a look at the capacitor then. What if we were to do the opposite? This time, we're going to increase the XC of the capacitor. Okay, if I increase the XC, would that cause the current through the capacitor to decrease? The current through the capacitor would decrease, causing a VAR value of storing and releasing to also decrease, which would then mean that our horizontal power triangle for the entire circuit now looks a little bit like this. There is more inductive reactive VARs because this has shrunk in value. And because of that, what happens to the total S or VA of the circuit? It's gone up, hasn't it? S total would go up, which would then mean what? I total has also gone up. Okay, well, let's look at the next item. What about if we decrease the XL? Okay, we decrease the XL. Are we going to get a current that's smaller than 10 amps? Well, if you decrease the XL, what happens? If you decrease XL, then that means that the current would go up. And what would happen to the VARs of this? Well, the VARs would get larger. And so that would mean that we would again see a larger value of the inductive VARs. Power would remain the same as it has throughout all of our different situations, and the S total would again go up, causing an increase in the total current. It would It would spike higher than 10 amps. Okay, well, what would happen if we decrease the capacitive reactance of the capacitor? Decreasing the capacitive reactance would cause an increase in current, which would cause an increase in the VARs, just based on our calculations. So if the VARs goes up, that would mean that our power triangle would again look like this. More capacitive reactance or reactive VARs, because this value would be larger than this one. Power would remain the same in S total. Look at that hypotenuse. Yet again, man, it's getting repetitive. I total would also go up. Okay, what if we just took the inductor out? I'm just going to take the inductor out. What's going to happen? Well, power is going to remain the same, and QC is going to be much higher, right? Because that's all that's going to be left in the circuit, which means, oh, yet again, S total would have gone up, causing an increase in current. And then finally, just for giggles, let's say we remove the capacitor instead. Well, if you remove the capacitor instead, what we end up with is this triangle. Power remains the same. Q of the inductor is the only one that remains, which means S total yet again increases and the I total increases. So I want you to consider the implications here. If we were to have a situation in parallel where we had two of these three, let's take a moment and just consider the implications. Let's say we had a circuit where our resistive component was 1 ohm and our our inductive component was 1 ohm of inductive reactance, giving us these values of current, as in the previous example, of 10 amps. 10 amps and 10 amps. Now, if these are pure inductor and pure resistor, then that means that I've got 10 amps at 0, and I've got 10 amps at 270 degrees. If we were to work out the total current here, which we know we can do with mode 3 or an HV table, or honestly, I mean, really, you could just do it with Pythagoras, because these are pure values, which would then mean that the current value would be 14.14 amps. Whoop, there we go, 14.14 amps. In this situation, the source must deliver 14.14 amps to the circuit. What if you were to connect intentionally a capacitor? So we're kind of approaching it from the opposite side now. We're saying we originally had a circuit that was composed of all of this here. And now what we've done is we've decided, okay, since we understand the correlation of current values and out-of-phase components, I should be able to add a capacitor here. And by adding a, let's say, 10 amp capacitor, what will that do? When I close the switch, when the switch is closed, what will happen to the total amount of current that my source must provide to the circuit? And you're right. I mean, it's exactly what happened in our previous pages of unity power factor in a parallel circuit. If I close this switch, what happens? Well, we get the example that we just looked at. What happens to the current? The current goes down. When the switch is closed, the source now only has to provide 10 amps. And this process here is then referred to, it's advantageous to do, and it's referred to as power factor correction. And why would I want to do this? Why would I want to do this? Well, I want to do this because I can lower the current from the source. If I can lower the current from the source, I mean, this is fantastic. Have I affected any of the watts at all? No. Take a look in the previous examples. Of course not. The watts are resistive in nature, and the resistance and the current through the resistor hasn't changed by throwing the switch. Now all that happens is that we would have current that is playing a game of catch and release between the capacitor and the inductor as they store and release energy at completely opposite times within the sine wave. So what's the purpose of power factor correction? To lower the amount of current that the source has to provide. And the source, really, I mean, what is the source? We say the source in quotation marks, but the source is actually BC Hydro. So interesting considerations and implications in the AC world when we use capacitors to help reduce the overall current of the circuit. And that brings us to the end of our discussion on parallel unity power factor circuits.